Welcome to video instruction on implicit differentiation. At this time, you should have already filled out the definitions of explicit and implicit functions and have an understanding that an implicit function is one in which you can't solve it for y. Now, the process of taking the derivative is going to be a little different for that reason, and here are the steps involved that you can refer back to when you're doing some problems on your own. We're going to go ahead and go through the process with just some examples. And the first one that has been selected is looking at assuming that y is defined implicitly by this equation, which is the equation of a circle with radius of 5. It's asking you to find dy dx, which is the rate of change at any particular point on this circle. So now if you think about it, every single ordered pair on this circle has an x and it has a y coordinate. But the x value will also have another y value associated with that. If you were to try to solve this particular function for y, you would find that you would get y squared is equal to 25 minus x squared. And when you try to solve for y and take the square root of both sides, you would get y is equal to plus or minus the square root of 25 minus x squared. Hence, two separate equations, one for the top of the circle and the other for the bottom of the circle. So instead of taking the derivative twice, we're going to use implicit differentiation with the original equation not solved for y, and this is how the process goes. Okay, starting out, let me go ahead and rewrite it over here. What we're going to do is when when you have a term that only involves x, you can go ahead and take the derivative like normal. So it would be 2x for that particular term. So we're kind of going through a structure rule where you have a f of x plus a g of x, if you will. What I want you to think of is I want you to imagine that y is some function of x, but we don't know what it is, and it's holding place with y. So in that case, what's going on is that you've got some function and it's being squared. So anytime y is involved in these equations, you can consider that it's a chain rule that you're going to have to apply. So think of y as your inside function and it's being squared, so the outside function is x squared. So we're going to take the derivative of the outside function, holding place for the inside function. So it would be subtracting 1 from there, which would be 1, which I'm not going to write. So you would leave y left unchanged. And then we're going to chain on the derivative of y, which since we don't know what it is, we're just going to denote it as dy dx, which basically is saying, hey, once we know what y is, this represents its derivative. Equals then, taking the derivative on this side is going to be 0. Now, if I were doing all proper notation, which I'm not, I would have I would have written d dx of x squared, d dx of y squared, and d dx of 25, kind of like you're taking, not kind of like, but you're actually taking the derivative of both sides of this equation. So if it's a constant, the derivative is 0. So that's our first round through this. Now, once you get to this spot, what you're going to need to do now is solve for dy dx. So that would involve bringing the 2x term to the other side. So I'll write it out step by step. And hopefully, depending on your algebra savviness, you could maybe do it all in one swoop, okay? So this would be negative 2x. And then we're going to go ahead and divide both sides by the 2y to get dy dx all by itself. So when you do this, obviously these simplify to equal 1, and you get dy dx is equal to the 2 simplified to equal 1, and you get the opposite of x over y, which is then the equation to find the slope not just at x but at y. So in this particular case where you see you have this x, that's the same x, but this is y from the top equation and this would be y from the bottom equation. I'll call it y sub 2. So in this case, maybe you had 3 and 4, and this one would be 3 and negative 4. So you'd fill it in, and what would happen is up here you're going to have a negative slope where both of these values are positive, and here, since one of these values is going to be negative, that would become positive, and it's just basically opposite sign for your slope. All right, that's the first example, and we'll continue on. All right, example number 2 says, assuming that y is defined implicitly by this equation, find dy dx. All right, so I'm going to rewrite it here. And as I rewrite it, I want to point out this first term is just in terms of x. This second term is just in terms of y. And on the other side, we've got 6xy, which is a product rule between two functions. And I'll explain. So first of all, get out of there. Go away. Okay, we're going to just call this 6x the first function and the y the second function when we're carrying out our product rule. Now your structure rules all still apply, and you're just going to be using the chain rule in a very different way. Remember, we're going to think of y as some inside function that we don't know what it is, and it kind of makes implicit differentiation a little bit simpler because you don't have to remember your function rule. You just hold place with it. So here we go, left to right. Remember, well, actually, I'm going to write it out just once, okay? All right, so on this side, we're going to be taking the derivative with respect to x, okay? And on this side, we're going to be taking the derivative with respect to x, which I should have written, nicely. But so that's what you're doing, in which case you would take the derivative of this term, and then the derivative of this side. Okay, like I said, I'm not going to write that again, but just know you're taking the derivative of both sides of this equation. And this term that only involves x is going to be like you normally do. This one, you're going to think of y as an inside function, so there's a chain rule with x to the third as the outside function, so its derivative, it would be 3 holding place for the inside function squared. So that's the template for the derivative of the outside function. Leave that inside function unchanged. Times then, to write the derivative, some people do write it as y prime, so if you ever see that, that's not unusual. We're just going to use Leibniz notation. It's indicated here, so that would be you're chaining on the derivative of that inside function, which is dy dx. Okay, so we're done on this side. Now again, on this side, we've got a product rule going on, so don't forget product rule. Structure rule is f prime g plus fg prime, in which case f is the first function from left to right. Really, there's no significant difference between them. It's multiplication and it is commutative, so you can use either one. Anyhow, here we go. You're going to take the derivative of 6x, which is 6, times y left alone, plus then 6x left alone, and now you're taking the derivative of y. Notice that it doesn't have a squared or any other function going on with it, so it's just kind of like it's a function without no chain rule. So here again, we're writing the 6x. So to write the derivative of y, you're just going to say dy dx. There's no chain rule because there's no other function going on with that. All right, there you go. Okay, now at this point, what you're going to do is solve for dy dx. So you're going to want to get dy dx terms all on one side. So these are your dy dx terms. I'm going to bring them all to this side to the left and then all other terms to the right, all in one swoop. This is my word now. Okay, 3y squared dy dx, and then bringing over the minus 6 dy dx. And then the 6y is over here, and we're going to subtract the 3x squared. All right, now to get it down to just having one dy dx, we're going to factor that out. So you're going to have dy dx out here, and that would leave 3y squared minus 6x in the quantity. And yes, you guessed it, in order to solve for dy dx, we're just going to take this side here and divide it by this. So I'll write it all out nice and pretty. And it will be 6y minus 3x squared all over 3y squared minus 6x. Okay, and that is success. Okay, moving on to the next problem. Now, on this problem, it's saying, assuming that y is defined implicitly by this equation, find dy. Now, this is the notation. This is Leibniz notation asking you to find dy dx and then evaluate it for this ordered pair. So notice they're giving you an x and a y value in this ordered pair because these implicit formulas for the slope involve both x and y. So it's asking you for the slope of the tangent to the curve at that particular point. Okay, I would like to pause the video and give you a chance to do it on your own. I know that it has a trig function in it. So just give it a chance and I will come back with all of the work and still talk you through it. All right, go ahead and check your answer. Did you get this for the slope formula? And did you fill in the one pi over 2 and end up getting this. Okay, well, if you didn't, you can look through the work, but I'm going to talk you through real fast. This first term is a product between 2x and y. So the derivative of 2x is 2 times y left alone, 2x left alone, derivative of y is dy dx. This is just a constant multiplier, and you have a chain rule with the sign being the outside function. So you just have pi. Take the derivative of the outside, which is sine, which is cosine, leaving the inside function unchanged, then chain on the derivative of y, which is dy dx. And the derivative of 2 pi being a constant is just 0. So here I factored out dy dx out of these two terms here, brought the negative 2y over, and then divided. So hopefully that makes good sense. Let's move on to the last example, number 4. And same thing. I'm going to let you go ahead and try it. I'm going to pause the video and fill it in. Good luck. Okay, so hopefully when you took the derivative, you found this. And if not, just go through the work, see if you can check, pause the video, see where you went wrong. Once you get that, you want to go ahead and fill in -4 for x and the 2 root 3, and be very careful with all of this arithmetic to get down to the slope, and then fill it in since it asks for the equation of line tangent to the curve. So here's the point, they've already given it to you, and you just found the slope. And there it is. All right, that is implicit differentiation. Go on to do your practice problems, and bye-bye.